Good day and welcome back to the final part of our discussion on triple integrals. In this video, I would like to go over one additional example, kind of involving visualization, triple integrals, and hopefully set the stage for something that's going to come in our next section. What we would like to do is find the volume of the solid bounded by the surface x squared plus y squared equals 9, y plus z equals 5, and z equals 1. And of course, our first step is to draw pictures. Let's put a little bit of terminology to these surfaces. X squared plus y squared equals 9 is a standard cylinder. Radius 3 wraps around the z-axis. Y plus z equals 5 is a plane, and z equals 1 is also a plane. So let me kind of just walk you through my thought process, how I would sketch this solid. Once we have a picture of the solid, we should be able to somewhat efficiently set up the triple integral. Starting with the cylinder, x squared plus y squared equals 9. It intersects the z equals 0 plane precisely at this circle of radius 3 centered at the origin, and we have this cylinder that wraps around the z-axis. This is what we typically would visualize as a cylinder. Now, the cylinder is going to be bounded in some sense above and below by these planes. Note the first plane, z equals 5 minus y, which is visualized most easily by thinking about that x equals 0 trace. So note when x is equal to 0, you would be flat in the yz plane. And you would intersect the z-axis at 5, and it's a line with slope minus 1 when you're going in that positive y direction. So roughly speaking, I'm just going to draw a dashed line to represent it. Similarly, the solid is bounded below by z equals 1. And z equals 1 is a horizontal plane that would cut off this cylinder at the bottom. So let's put this together, and I'm going to get rid of some of these lines. Note our cylinder is bounded above by this plane, z equals 5 minus y, and below by z equals 1. So the bottom of our cylinder is at z equals 1, and we go up this cylinder until we hit that upper plane of z equals 5 minus y. And if we cut off the cylinder at kind of this diagonal, we just get a diagonal end cap, in a sense, to our cylinder. So in red, we have a representation of this solid. So note, just to add in a little bit of depth, we can think of the top of this as being the plane z equals 5 minus y, and below we can think of it as being z equals 1. And we should be in an ideal situation now to set up this triple integral. So the volume of E would be the triple integral over E of the function 1. And what we need is an outside double integral and an inside single integral. And we see that our solid varies very nicely in that z direction. You're varying from z equals 1 up to hitting that upper plane. So in that z direction, we're varying from z equals 1 to z equals 5 minus y. In terms of the double integral, remember in this case we would compact that down into the xy plane. And when you do, you get your region D, which is this circular disk centered at the origin. And because it's coming from the cylinder, x squared plus y squared equals 9, we know precisely what disk it is. And when we see something of this form, hopefully we immediately now think of polar coordinates. So in polar coordinates, we'd want to say the r values vary from 0 to 3, and the theta values vary from 0 to 2 pi as we go all the way around. And to convert into polar coordinates, I'm going to first take care of the inside integral. The antiderivative of 1 is z. We substitute in 5 minus y, we put a minus sign, and we substitute in 1. That is to say it's the double integral over d of 4 minus y. And to convert it into polar coordinates, remember the y is going to become r sine theta, the dA becomes r dr d theta, and we add in limits of integration. So we would have 4 minus r sine r dr d theta, r on the inside from 0 to 3, theta on the outside from 0 to 2 pi. And leaving a few details to you, which you can hopefully work out fairly quickly, you should end up with a volume of 36 pi. And for now, at least in terms of Cartesian coordinates, this finishes up our discussion on triple integrals. What we are going to see in the next few sections are two different coordinate systems that we can use. Something called cylindrical coordinates, very similar to what we've done here, and then after that, something called spherical coordinates. So stay tuned and take care.